Hey everyone, let's talk about the theorems of Pappus-Guldinus, and I apologize if I'm not pronouncing those correctly. So these are two theorems that tell us a little bit about what happens if we take a curve, okay, an arbitrary curve. In this case, my arbitrary curve is a thin ring, and I'm going to rotate it around a central axis. Okay, so this is going to be, I'm going to create a body of revolution. Okay, and what the first theorem tells us is that if I take this curve and I rotate it around the body of revolution, right, 360 degrees, I'm going to create a shape. In this case, it would be like a donut, but it would be a hollow donut. All right, and we're going to think that this is infinitely thin. So I'm going to create this hollow donut. All right, it's what's called a torus. And I'm looking just at the surface area of the torus. Okay, so the surface area of the donut. So if I was thinking about this with a donut, I might be interested in how much sugar do I need to cover this surface area? And so I need to know what that surface area is. And what the theorem says, this is the first theorem of Pappus-Guldinus, what the theorem says is that the area, the surface area, created by taking this curve, okay, in this case it's a circle, but it's still a curve, is equal to the centroid times, well, the length that the centroid undergoes. So the centroid is right here in the middle, so that's going to have some value x bar. If I'm the y-axis, and this is on the, well, let's go over here. This is on the x-axis. There's going to have a value x bar, and I'm going to rotate around the y-axis. Okay, I'm rotating around the y-axis. And so I create this, you can think of it like as an inner tube would be another way, like a big truck inner tube. What's the surface area of that big truck inner tube? So it's going to be the circumference created by the centroid. So the centroid creates a circle. As you make that revolution, it's going to create a circle. So it's the circumference of that circle times the length of the curve. In this case, the length of the curve is also a circle. That's maybe a bad example. Maybe I shouldn't have used a circle, but there it is. So it's going to be the circumference of this circle times the circumference created by the centroid. But in general, the surface area is equal to 2 pi times the centroid. I'm going to put x bar. So the centroid, if I'm rotating around the x-axis, around the y-axis, it's the x position of the centroid. Right? If I'm rotating around the x-axis, like this, then it's the y position of the centroid. Okay, so 2 pi x bar times then the length of the curve. Okay, so this is the let me call it this. Let me say it's the distance. Maybe I'm going to say the perpendicular distance from the axis of rotation to the centroid of the curve. And this is equal to the length of the curve. Okay, so generically I might have, let's say, a curve here. And if I'm rotating this around the y-axis, this curve, this function, will have an x and a y position of the centroid. And let's say that that's right here. Okay, so that's x bar, y bar. Then when I rotate this shape around the y-axis, right, this is the x-axis, this is the y-axis. When I rotate it around the y-axis, I'm going to take the length of this curve, and then I'm going to multiply that by 2 pi times x bar, because I'm rotating around the y-axis, and that's going to give me the surface area of that shape. That's going to give me the surface area of that shape. If I rotate it around the x-axis, then I would take the length, same length, but in this case it would be 2 pi times y bar instead of x bar. All right, that's the first theorem. Now the second theorem is really very similar, except we're going to be talking about volumes. So let me take this area, if you will. So I'm just looking at this area, and the x position of that of the centroid of this area, the x position of that centroid is at some x value. And when I rotate around, I'm going to get a donut again. But now I'm interested in the volume of the donut. I want to know the volume of the donut. And in a similar fashion, it's really basically the same equation, but the volume of the donut, right, V is for the volume, is 2 pi times x bar. Again, that's the perpendicular distance from the axis of rotation, the centroid. And I say it that way in case I were to rotate it around this point over here, right, if I shifted the axis of rotation to a different point. And then I'm going to multiply that by the area, in this case pi r squared. So the volume would be 2 pi x times the area of this circle, right? 2 pi x times the area of that circle. Well, let me give you a similar example. Remember when we did in a previous video, we found the centroid of a half ring, right? The inner radius of the ring was A, the outer radius of the ring was B. Okay, hopefully you remember that. So the inner radius was A, the outer radius was B. Right, so the ring looks something like this. And we fill this in, right? And we discovered that y bar for this shape was equal to 4 over 3 pi, and then b cubed minus a cubed over b squared minus a squared. So let's say that's somewhere like right here. Okay, then if I were to take that half ring now, forget the bottom part, and rotate it around the x-axis. Okay, I'm going to rotate it around the x-axis. I'm going to create a volume because this has thickness. Right? This is not a curve. It's not the thickest of rings, but it has thickness. So I'm going to create a volume of revolution. It's going to be something similar to a sphere, right? So I'm going to create a volume of revolution. And the volume of that volume of revolution is going to be equal to, so the volume of that is going to equal 2 pi times y bar times the area of this, times the area of that thick ring. All right, so 2 pi, y bar, though, is 4 over 3 pi, and then b cubed minus a cubed, b squared minus a squared. And then it's a thick half ring, right? A thick half ring. Well, let's see. So the area of a circle is pi r squared, and so it's going to be pi r squared. That's going to be b squared. But then I'm going to take away, right? I'm going to take away a squared, because b squared would be the entire semicircle. Then we take away the other semicircle that's underneath. So b squared minus a squared. So pi r squared, but then it's a semicircle, and so I'm going to divide that by 2 because it's only a half a circle. Right? And so notice the b squareds go away. Let's see, what else is going to happen here? So the b squared, those are going to go away, and I'm going to get the 2's go away. This pi cancels that pi, and I get 4/3. There's a pi, that stays around, and I'm going to get b cubed minus a cubed. Well, what is that? That's the volume of a sphere, of a thick but not complete sphere. Think of it this way, it would be like a basketball, where the outer radius of the basketball was b, and the inner radius of the basketball were a. Right? 4/3 pi r cubed is the volume of a sphere. Right? That's the volume of a sphere. But what I have is a thick ball, a thick hollow sphere. So I've got to take away the inner part. So b is the radius of the outer layer of the basketball, and a is the radius to the inner layer of the basketball. And so I get the volume of a hollow sphere, a hollow thick sphere. Right? And that's exactly what I anticipated. All right? So that's how we can utilize the theorems of Pappus-Guldinus. I can use any shape, doesn't matter, any shape, and this will all work. All right. If you have any questions on that, please leave them in the comments below. Thank you.